have been looking at the classical linear regression model, the CLRM. We discussed the 7 assumptions of CLRM, and because of these assumptions, we were assured that the OLS estimators that were found, beta 1 hat, beta 2 hat, similarly sigma hat, these estimators derived using the OLS criteria had certain desirable statistical properties. They were blue, which means best linear unbiased estimators. So till now we were concerned with simply the numerical and statistical properties of the estimators. So as far as estimation of the linear regression model is concerned, these assumptions are more than enough for us to estimate a regression equation, right? But we have to remember that these estimators are based on sample values. So every time from the same population, when you take a different sample, because the individual cases of the sample might vary, the estimators will also vary from sample to sample. So this will mean that the estimators are themselves random variables, and random variables will be associated with some sort of probability distribution. So if we are content with just estimating the regression equation, we are still okay. But when we need to do some sort of hypothesis testing so that we can comment on or predict based on the estimated regression model, we need to make some additional assumptions regarding the distribution of these estimators, beta 1 hat, beta 2 hat, sigma hat square, and so on. Right? Only then can we comment on how close the estimated regression estimators are to the actual population regression parameters. That is, how close is beta 1 hat to the original beta 1, how close is beta 2 hat to the original beta 2, and how close is sigma hat squared to the original sigma square of the population regression function. So, in order to find out the probability distributions of these random variables, we know that beta 2 hat is a linear function of random variable yi, right? The dependent variable in our regression model. You will recall from the proofs that we have done that beta 2 hat can be written as summation ki yi, where ki is nothing but xi divided by summation xi square, right? So further, yi can be written in the original population regression function form, that is beta 1 plus beta 2 xi plus ui. So what this means is, recall our assumption from CLRM, which says that all x's or the x values are considered to be non-stochastic. So if your capital Xi values are non-stochastic, that would mean that deviations, that is small xi values, are also non-stochastic. In this case of beta 2 hat, in the formula of beta 2 hat, my ki is a function of small xi. Since x values or the x variables are considered to be non-stochastic and ki is a function of these x variables, ki is also non-stochastic. By non-stochastic, I mean not random, right? They are fixed or they are set. So when I expand yi as beta 1 plus beta 2 xi plus ui, I can see that beta 1 plus beta 2 xi of the population regression function, that part is again non-stochastic. So in the second In this second equation, ui is the only stochastic part in the entire expression of beta 2 hat, right? So beta 2 hat is ultimately a function of the stochastic error term. Once again, remember, ui is called error term, it is called the disturbance term, it is also often called deviation between observed and estimated y values, right? So since beta 2 hat is ultimately a linear function of random variable ui, the probability distribution that beta 2 hat follows will depend on what is the probability distribution of the error term ui. And we know that beta 1 hat is a function of beta 2. How is it a function of beta? So beta 1 is equal to y bar minus beta 2 hat x bar, right? So even beta 1 is a function of, or beta 1's probability distribution will also ultimately depend on the probability distribution of ui, or the error term. So for the purpose of making any sort of inference about the population regression function from the sample regression function, we need to make some assumptions about the probability distribution followed by the error term ui. What is that assumption that we make? We assume that our error term ui follows a normal distribution, and that is how from my CLRM I introduce an n and I get classical normal linear regression model, or the CNLRM. Now, the details of the normality assumption of ui. It assumes that the CNLRM, that is the classical normal linear regression model, assumes that ui is distributed with normally, as a normal distribution with mean. We know our mean is expectation of ui equal to 0. This is also a part of our CLRM assumptions. And what are the variance? The variance, remember, this is the formula for variance. When you talk about random variables following certain distributions, this is how we calculate variance. Expectation of deviation from mean squared. So ui is the value, e of ui is the mean error term, and this deviation is squared. Expectation of deviation squared will be the variance. And we know that e of ui, that is mean value of ui, is equal to 0. So it is the same as saying expectation of ui square is equal to a fixed positive value called sigma square. It's positive because it's a square. Similarly, the covariance ui uj is equal to 0. Again, these are all a part of your CLRM assumptions, but we are saying that now we are assuming ui is normally distributed with this mean 0 and this variance sigma square, right? More properly, it is written as NID, that is normally and independently distributed. By independently, I mean the third point, that the covariance between ui and uj is equal to 0, right? So normally, NID stands for normally and independently distributed. Now, why do we use the normality assumption? Why not some other probability distribution assumption? There are a few justifications that we can present. Let's see. First is that we always think of ui as a proxy for all those variables that have not been explicitly included in the regression model, right? I'm sorry, there's a small editing here that have not been explicitly included, right? Okay, that's an editing, please note. So UI represents the combined influence of several independent variables which have not been explicitly included in my regression function. Why have we not explicitly included them? Because we are assuming that the individual influence of these omitted variables is very, very, very small and it's not at all systematic. So it does not serve any purpose to introduce them as a separate explanatory variable, right? Now we use the central limit theorem, it's called the CLT. According to this, if there are a large number of independently and identically distributed random variables, then the sum of these variables will tend to follow a normal distribution, right? Especially as the number of these variables increases indefinitely. We are actually in mathematics, we are talking of the terms of limit number of variables tending towards infinity. Okay, few of you might remember this concept from your quantitative economics classes. So the central limit theorem says that as the number of these excluded variables, as they keep increasing, and these variables are independently and identically distributed random variables, the sum total of their influence follows a normal distribution, right? Another variant of this central limit theorem says that even if the number of variables is not very large, or even if these variables are not very strictly independent, the sum of them may still follow normal distribution. So because of the central limit theorem, it is very reasonable for us, or it is very justified for us to assume that my error term UI follows a normal distribution, right? And a normally distributed variable has some other advantages associated with it. The next one is a point to be noted. See, any linear function of a normal variable will also be normally distributed. Now I showed you earlier how beta 2 hat is a function ultimately of my error term UI. Beta 1 hat is also ultimately a function of the error term UI. So since if we make an assumption about the UI or the error term, if we make an assumption that it is normally distributed, I can automatically transfer and make the same assumption that my estimators beta 1 hat and beta 2 hat are also normally distributed. This makes hypothesis testing much simpler. When we move forward, our next chapter is going to deal with all these sorts of hypothesis testing, right? Another advantage of assuming a normal distribution is that it is a very simple, comparatively simple distribution with ideal and very easy to handle conclusions. Okay, it can be described using only two key parameters, the mean and the variance, right? And even in nature and even practically and empirically, there are many phenomena that we tend to study which seem to follow a normal distribution. So using this assumption of normal distribution for the error term seems very reasonable, mathematically justified, and also very practical, because empirically a lot of variables, a lot of instances, a lot of phenomena follow a normal distribution, right? Another point to be noted is that when your sample size is less than 100 observations, that is, you have a relatively smaller sample size, this normality assumption helps you or allows you to use T, F and chi-square tests for the regression model. Again, it's a little technical, the explanation is a little technical, so just remember this point, that especially when it comes to small sample sizes, if we have assumed that the error term follows a normal distribution, it automatically allows us to use T, F and chi-square statistics. Okay. Now, if the sample size is reasonably large, then we can always relax this normality assumption and not affect the hypothesis testing. Okay, but in many situations we have small samples. So in these small samples, if we have to use T, F or chi-square statistics or chi-square tests, we need the help of this normality assumption, or we need to assume that error term ui is normally distributed. When it comes to large samples, a T statistic or an F statistic that is calculated based on the sample will approximate automatically to the distributions, T distribution and the F distribution. So again, it is very reasonable. It is very reasonable to assume that a normally distributed, or valid to assume that these T and F tests can be used when we are working on a normally distributed error term assumption. Once again, if we have very large data sets where the sample size is quite large, we can always relax the normality assumption without affecting the quality of our inference. Now, once you have made the assumption of a normally distributed error term with mean 0 and variance sigma square, what are the properties that the OLS estimators now have? Like earlier, they are still unbiased. Okay, even under CLRM assumptions, they were already unbiased. The OLS estimators after assumption of normality are also unbiased. Like earlier, even now they have the minimum variance, right? Now remember, minimum variance and unbiasedness together mean that these estimators, these OLS estimators are efficient estimators. So efficiency technically means unbiased and having the minimum possible variance. Now, both these properties we already had in an OLS estimator when we had the CLRM assumptions, right? So what is new? What does the new assumption of normality give us? The third property is the new property. The third property says that the OLS estimators are now consistent. What do you mean by consistent? It means that as the size of my sample increases, the estimators will actually converge to the true population values. Okay, this is something new. This was not present when we had the CLRM assumptions alone. When we added the normality of UI, normality assumption of UI, that is when we have got this new property that the OLS estimators will be consistent. Consistency means as the sample size increases, the estimators will converge to their true population values. Now, remember I told you earlier, since beta 1 hat is a function of UI, the normality property of UI will also come on to beta 1 hat. So beta 1 hat is also normally distributed. Its mean we know is the mean of beta 1 hat is equal to the population beta 1. Its variance also we have seen in the earlier classes. So remember, normal distribution will always be described by two parameters, the mean and the variance, right? So this is the notation, this is the technical notation. This is technically how we write it, where the first parameter beta 1 is the mean and the second parameter is the variance, right? Now another property of any normally distributed variable is that you can always define a variable z which is standard normal. That is, if I perform this mathematical operation, that is the estimated value minus mean divided by variance, what you will get follows a normal distribution with mean 0 and variance 1. This is called a standard normal distribution. So it's another added advantage of using the normal distribution assumption. Similarly, beta 2 hat is also a linear function of ui, and therefore it will also be normally distributed. Its mean will be equal to population parameter beta 2. Its variance, we have derived it in detail, is sigma square divided by summation xi square. So this is how you will write the technically write. It's normally and independently distributed with mean beta 2 and sigma beta 2 hat squared. Again, because it is normally distributed, you can transform this variable from beta 2 hat. You can find a variable z which follows a standard normal distribution. The importance of this convenience is clearer when we move into the field of hypothesis testing. Right? Another assumption is that, another property of the OLS estimator, this is with regard to the OLS estimator of the, that is sigma hat square. So n minus 2 times sigma hat square by sigma square. Please note it, I couldn't type it out properly. It will be written as n minus 2 times sigma hat square divided by sigma square. So sigma hat square is the estimated variance and sigma square is the true population variance. Okay, so the ratio of these variances will follow a chi-square distribution. N minus 2 is known as the degrees of freedom. Okay, similarly beta 1 hat and beta 2 hat, once again this is how it should look. I'm sorry, the printing was not properly done, the typing was not correctly done. So beta 1 hat and beta 2 hat are distributed independent of sigma hat square. And okay, 6 and 7 are very technical properties. Point 8 is the one which is more important. Once you make this additional assumption of ui being distributed normally, the OLS estimators beta 1 hat and beta 2 hat are now the best unbiased estimators. That is, they have the minimum variance in the entire class of unbiased estimators. Earlier, in the entire class of linear unbiased estimators, we had minimum variance. But now that we have included an assumption regarding ui, saying that ui is normally distributed, now even if they are not linear, in the entire class of unbiased estimators, my OLS estimators beta 1 hat and beta 2 hat have minimum variance. Right? Finally, just note that the assumption I made was ui follows normal distribution with 0, mean 0 and variance sigma square. And like we have been saying, since yi is a linear function of ui, even yi, that is even my dependent variable automatically is a normally distributed variable. What does it mean? The expected value of yi is beta 1 plus beta 2 xi. We have been dealing with this equation since the first class of econometrics. And what is the variance of yi? The variance of yi will be the same as variance of ui, isn't it? So it will be equal to sigma square. So just note that even when I make this assumption regarding a single variable in my regression model, that is regarding ui, even my dependent variable yi automatically becomes a normally distributed variable, right? Once again, in the following lectures, you can see how this relatively simple assumption helps us a lot in hypothesis testing. Thank you.